morning, AP Chem students. We're going to be talking about atomic orbitals today. This kind of piggyback right on what we talked about yesterday. So, orbitals are essentially just a location where we can find a probability, or a location where we have a probability of finding an electron, typically 90% of the time. Orbitals kind of denotes an orbit, but it's not really an orbit of like the moon orbiting the Earth. It's more of just a probability of a density where those electrons are found near the nucleus or further from the nucleus. So let's talk about these orbitals. First off, we have s orbitals that we're going to start with. These guys are spherical. They can hold a maximum of 2 electrons each, and we say n equals 1 and up, and this is, we're talking about a principal quantum number. We'll get more into principal quantum numbers in the next video, but for now we'll just say n equals 1. You'll find them in the first period starting and all the way up to period 4, 5, 6, and 7 going on. So you're going to always find s orbitals hanging around. Here's an example of a couple s orbitals. This is a 1s orbital right here. So you can tell it's a spherical orbital just like this in a 3-dimensional plane, x, y, and z axis. This is actually the 2s orbital right here. You can see that it's larger. Those electrons are spending more time away from the center of the atom, the nucleus there in the center. And then this is going to be a 3s orbital here. You can see it's even larger. So each one of these is only going to have 2 electrons max in it. So a spherical orbital. P orbitals are coming next. So we have p orbitals. These guys are dumbbell shaped, we can call it. We say that there is a max of 2 electrons each, but there are also 3 p orbitals, which gives us a total of 6 electrons. And we'll find these guys n equals 2. Principal quantum number 2. This is going to start in our second period. So the first time we're going to see p orbitals show up is for boron, atomic number 5, and so on. We don't see them in the first period because we're not going to have p orbitals in hydrogen and helium. This gives us an example of what this dumbbell shape looks like. Obviously right here in the center is going to be where our nucleus is. And so we have 3 different p orbitals. Each one of these is going to contain 2 electrons, so maybe you'll have an electron here, electron here. Again, probability density, they're going to be found 90% of the time inside of this area and sometimes outside of the area. And we've got 3 of them. We call them px, py, and pz. And that just denotes the 3-dimensional planes of these 3. I'm kind of going fast through this because I know this is stuff that we talked about in general chemistry. So if you need to watch this again, it'll be up on my website. You can always watch it when you get home. D orbitals are coming next. These guys look like 4-leaf clovers for the most part. Sometimes they don't. We see these in n equals 3. They actually start in the 4th period with atomic number 21. We have 2 electrons in each one with 5 of these guys, and so we have a max of 10 electrons. And these are kind of what we're talking about with this 4-leaf clover designation here. There's our 4-leaf clover. So we have 4 of them on the different axes, and then there's this one that looks kind of strange, but it's still a d orbital, and it still is only going to have 2 electrons. So if we have 2 electrons each, that's going to total up to a maximum of 10. And like I said, we see those starting at atomic number 21. F orbitals have this complex shape. We see this n equals 4 and up. Max of 2 electrons per times 7. So we're going to have a total of 14. And then you can kind of see what's going on with these shapes here, some unique looking shapes here. Don't worry about what these values here mean. We'll talk about that later. Okay, so that's just an overview of our different orbitals, and let's talk about how we place electrons so we can get an idea of what the electrons are doing, which is so important for bonding in both ionic and covalent bonding that's coming very soon. So let's talk about electron configurations in the periodic table. So if we look at our periodic table here, the periodic table, the really nice thing about it is it organizes how these electron configurations set up for us. So give you an idea of what we're talking about here. Up here we have period 1, and we were talking about n equals 1, and this is going to be 1s1 for the hydrogen, and then we have 1s2 over here for the helium, and we knew that. We just fill in those 2. Remember, s orbitals can only hold the maximum of 2 electrons. And then we jump down here in n equals 2, period 2, and this becomes our 2s block For lithium there we have 2s1, beryllium 2s2. Then we jump over here to boron, and like I said before, boron starts our 2p block, and this is our 2p block. Remember, p orbitals can hold 6 electrons. We have 3 orbitals holding 2 each for a maximum of 6, and notice how we have 1, 2, 3, 4, 5, 6 atoms over here, or elements over here. And so there's our 2p block, and then we drop down here to our 3s block, and then there comes our 3p block. So we can make predictions really easily. There's our 4s block. Jumping in here, here's atomic number 21, and so remember we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and these are going to be our 3d orbitals. Now, really important to note that these 4s's tend to fill first, and then we're going to go into the 3ds, which does drop down one. And then we get over here to gallium, and atomic number 31, and this goes back to our 4p block. So a real common mistakes students make sometimes is they'll say an element like calcium has 4s2, which they're correct, and then they say Sc, scandium here, and they'll say this is a 4d, and it really isn't. It actually drops back down to 3d. Another common mistake students make is they get to the end of 3d at zinc here, and then they'll say the gallium is 3p, but remember we've already used up 3p over here. And this just keeps on repeating over and over again. There's our 5s, there's our 6s, there's our 7s, and so on. And then we jump in here to the f orbitals right here. Remember these intertransition metals, the lanthanide and actinide series, are pulled out of the periodic table right there. So this is where we come in with our f orbitals. And we can use this to predict what's going on when we're drawing electron configurations, which is really important. Rather than just looking at electron configuration, let's say for this guy right here, 76, we can make a prediction about what's going to happen here. And we know there's some D's going on here. So let's talk about electron configuration as well as noble gas electron configuration. This is what you're going to do some practice on today, both of these things. So we're going to start off with germanium here, GE, and I go back up here and I look, and germanium is sitting right here. I'm going to kind of highlight this in blue. Got a whole bunch of other things on my screen here, so let me erase a few things off here and just get things cleaned up a little bit. But GE is going to be right here, and it's atomic number 32, and that's what we're going to look at right now to do an electron configuration. So one thing we can do is we know we're going to end up period 4, so there's a 4s right there. We know we're going to have some 3ds involved, and then we have 1, 2, so this is going to be 2p, 3p, 4p, 2 is where we're going to end up. So let's go ahead and do the shorthand notation or electron configuration for 32 for germanium. Again, this guy is atomic number 32, and so we're going to say, we're going to start with the lowest energy, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. And remember I said we were going to end up at 4p2. And we go back up there, and that should be, yeah, we're right there at 4p2 there, because we're in the fourth period, n equals 4 in our p block. So that's how we do electron configurations that way. It just makes things really easy. And it is okay to write these guys with a 4s here and then the 3d there, although occasionally on tests and in books or something you'll see this 3d pulled over, and they'll flop these. You just have to remember that 3d is going to fill after the 4s there. Another way to write these electron configurations is we can do what's called noble gas electron configuration. This is a kind of a shortcut. So let's do this for germanium as well. And I'm going to kind of go back up here again and just erase some things off here, clean some things up. There we go. Okay, so now what we do for for noble gas electron configuration is, again, germanium is right here, and we're going to go backwards to the previous noble gas. So that would bring us all the way back this way. We got potassium, and then our previous noble gas is going to be argon. So what we'll do as a shortcut is we'll just start with argon. and we'll put argon in brackets, and that denotes that this is a noble gas electron configuration, argon, just like that. And then we'll start from there. So if we start from argon here and we jump down here to potassium, this is in period 4, n equals 4, and so we're going to say, okay, so we go 4s2, there is our potassium and our calcium taken care of, and then we're going to take care of our 3D block. We'll throw our 3D block in here, 3D10, that takes us all the way out to zinc right there, and then we just have 2 more to go, and we're in our 4p block here, and we have 1 for gallium, 2 for germanium, and so we just do 4p2. So essentially these two mean the same exact thing. All I've done is I've just listed out these guys right here, and then I've thrown argon in front of them, and basically argon means all of those guys, because that is argon essentially, because we have 2, 4, 10, 18 electrons taken care of there, and argon does have 18 electrons. So that's how we're going to do electron configuration, noble gas electron configuration. You are going to have another video that's going to talk about quantum numbers here, but you're going to do some practice on it first. So tonight's video will be about quantum numbers, so we'll give you some homework, and if you just happen to finish early in class today, we'll go ahead and start that video.